Thank you so much. My name is M.Fogelson, and I will be presenting The Expanse, Advances in Design, Optimization, and Simulation for Linkage-Based Systems. First, thank you so much to my advisors, Zach Manchester and Jonathan Kagan, as well as my committee members, Min-Chen Lee and Jeff Lipton, as well as everyone that came here in person and all of the amazing friends and family on Zoom. Now, robotics talks typically start with these aspirational videos of biological systems like this ibex climbing up a sheer rock face. They're usually followed by a pitch that if only we had better artificial intelligence through control policies or faster compute or larger machine learning models, we would be able to achieve these agile behaviors today. But I think that's only half of the equation. I'm going to show you my favorite biological inspiration video of this fish swimming upstream. Now, the kicker is that the fish is dead. There's no control policy. There's no actuation. There's no models. And yet, this amazing behavior emerges from its interaction with the environment. And this is what I'll refer to as physical intelligence. These behaviors emerge from geometry, structure, and composition for animals to be able to be efficient and achieve these incredible feats. One amazing example of this physical intelligence realizes through Theo Jansen's walking sculptures, the Strand Beast. These are systems that are powered only by wind, but effortlessly walk across the beaches, which is still an advanced problem for robotic systems today. And they achieve this through these amazing linkage systems that effortlessly and naturally create these gates that are able to traverse this difficult terrain. Now, as I mentioned, physical intelligence is only half of the story. When we combine physical intelligence with artificial intelligence, like the Salto robot developed at UC Berkeley, we can see these systems jump to new heights, bounce off of walls, reorient themselves mid-air, and land with precision. So why don't we see more interesting and diverse sets of robotic designs in the real world? Why is everyone converging to these simplified forms of humans and dogs? It's because physical intelligence is hard. The composition of the structures and the boundary conditions that they provide for challenges for engineers to develop these systems. The optimization algorithms that we have don't scale well to the high dimensional design problems that persist. And the simulation tools that have been developed can only support these simplified robotic models, and so they can't handle the complex designs from the Salto or the Strand Beast. Where we do see some interesting developments in physical intelligence is in the outer space realm due to the harsh constraints and the specific tasks that we need. And this is kind of realized through the amazing development of James Webb that deploys to the size of a tennis court, and its segmented mirrors and optical instruments deploy with precision using these linkage-based structures. Now, it wasn't that James Webb came without any faults. There was tons of iteration and manual testing, making sure that all of these systems were going to succeed, as we can't have human intervention when we get into outer space. And even with all of this, there was over 100 single point failures that could have caused the mission to fail completely. And the development of James Webb was 14 years over the timeline and $9 billion over budget. So how can we get our space projects on time and under budget and support the design engineers that are developing these next generation systems? And that's where we'll be leveraging design optimization. These are tools where we leverage algorithms to be able to support the engineer in developing, testing, and analyzing structures that could be used for next generation systems. We're going to leverage these kind of standard mathematical formulation to describe this broader set of problems. And I know everyone's eyes just glazed over when we added some math and there's no more videos. So let's walk through what optimization is together. We're in effort trying to minimize or maximize some task or goal or objective. And in the real world, we have constraints. We have to obey the laws of physics or the design geometries. But we also have these knobs that we can turn to find these solutions. We've got continuous parameters, which are these smooth knobs where we can pick any possible value between infinite choices. And we've got these discrete parameters that make these jumps between different possibilities. And so a lot of my family just came from Indianapolis and went to the recent Indy 500 race. So I thought I would ground some examples of design optimization in something that they might understand more clearly. So an Indy car team trying to optimize a wheel for the upcoming race might want to minimize the track time and gas, making sure that the design obeys the laws of physics and the manufacturing and design limitations set forth by the competition. And some of the parameters that the engineer might be able to use is the location of the wheels. Can we extend the wheelbase or widen it? Or discrete parameters like the material of the wheels. Like if it's rainy like it was today, do we need to use a different tread? And so those are the choices that we have to make. Another quick example, looking at if the designers are looking towards a suspension design, well, now maybe they need to obey different constraints like the linkage degrees of freedom or the link lengths and the linkage configuration. And so this seems pretty easy, right? I can write this problem in this formulation and, hopefully we can use existing solvers that just pops out the answer. But actually there's many challenges with design optimization, particularly when we introduce these discrete parameters. The problem can explode computationally and lead to the what we call as NP hard, which literally means it can take forever for us to find the optimal solution. So in these cases, we want to find efficient solutions that satisfy all of our constraints and help the engineer move forward. The simulation tools for us to obey the laws of physics can't handle the complex linkage mechanisms from the Salto and the Janssen robot, leaving us with these simplified serial chain structures that relies more heavily on the software to allow the agility. And then finally, the biggest problem with optimization is that they're approximate by nature. And so when we need to translate the solutions into a realized product, there are many gaps because of unmodeled aspects. And this leads me to my thesis statement. Advances in robotic mechanical design through linkage-based structures offers new capabilities and applications. To make these designs more widespread, contributions are needed in their composition, their optimization, and their simulation. This work demonstrates how hierarchical composition enables mechanically stiff structures with high extension ratios, how the novel optimization techniques that we propose can find high-dimensional task-driven designs that satisfy the physical constraints, and how we can leverage data in differentiable simulation to provide new digital twin tools, modeling transient behaviors and phenomena such as jamming. So over the past 5 years, I've been very lucky and fortunate to publish works in a variety of robotic and aerospace conferences and journals. And today I'll be talking about many of them to show you how they come together in an effort to push forward the advancements of designing physically intelligent systems through linkage-based structures. So let's start with the math up front and look at scalable optimization formulations for actuator placement problems. Now, in this work, we're going to be looking at the example of James Webb seeking to point at the various stars and galaxies that we wanted to once it's deployed in space. And we presented a new method for solving these problems called CAPO, which is a control and actuator placement optimization. So just to ground this mathematical roots again, we're seeking to minimize the effort and number of actuators so that we can support longer missions and reduce weight and cost. We want to make sure that our design obeys the laws of physics and obeys any thrust and design limitations. And the knobs that we can turn in this optimization problem belong to the state trajectory, control input, location of the actuators, as well as the number and type of actuators. What we'd like to get out is an actuator placement and a control policy that can achieve the design tasks set forth by the engineer. So we make a couple assumptions in this problem to kind of simplify and make it tractable to to the algorithm. And the first one is that we assume that this complicated structure is represented as a bulk model of rigid bodies connected by flexible joints, and that there's a dense set of actuators placed along those bodies a priori by the designer. And we want to find the minimum set of these actuators that can achieve these particular tasks. So while this kind of general formulation was nice, I think it would be helpful to dive a little bit more specific into the exact problem that we're solving here. And don't worry, we'll continue to walk through this. There'll never be math without any sort of pictures or descriptions. So in this particular problem, we represent the state as the position, orientation, and velocities of each of these rigid bodies. We can update the control effort of all potential actuators. We introduce this actuator selector vector, which tells us, does an actuator exist or does it not exist, and the actuator positions. Our nonlinear dynamics is us saying we need to obey the laws of physics, and there are inequality constraints related to thrust limits or other design issues. And we need to make sure that either actuators do exist, so they're equal to 1, or they don't exist, they're equal to 0. We could also have written that an actuator doesn't exist by looking at the time-varying control effort and setting it equal to 0. However, this can be quite hard to write down as a constraint, and so that's where we introduce this beta term to allow us to easily decouple the actuator selection and control problem. Now, to solve that original formulation for high dimensions can take forever. And so what we do is we make several relaxations so that we can solve the problem more easily, showing that we can still find constraint-satisfying solutions. To that end, we first relax that existence and non-existence constraint and say it can be anywhere between existence and non-existence to make sure that we're able to then support the reduction of the actuators and project the solution back onto the original problem. We introduce this regularization term, which through the gradient helps us drive parameters down to 0 when they're not needed and somewhere non-zero when they are being used. This is called the lasso trick. However, when we get the solution from that formulation, we need to make sure that it satisfies the original problem of existence and non-existence. And what we can do is we can project by rounding up those values. So first we project the control outputs through the actuator selector vector, and then we can round up our beta, making sure that the actuators exist or don't exist again. And this projection we show still satisfies those original nonlinear dynamics. And so we are happy. However, if we just optimize over one particular task, like pointing at one galaxy, now that design that emerges might overfit to that specific problem. If there's variations or alternative tasks that we want to do, we need to kind of look at a set of the potential opportunities, and we can leverage the sparsity of the problem to make sure that we can still solve these optimization problems very efficiently. So we compare our method, CAPO, against a genetic algorithm and mixed integer nonlinear program. And what we'll show is that CAPO is the only scalable solutions for these high-dimensional problems. Now, this formulation is amazing because it generalizes over more tasks than just the James Webb pointing problem. It works for a variety of different design optimization problems, like an acrobatic multirotor, design of actuator placement for a large flexible space structure, even can be shown to work for configuring robotic arms for manipulating cloth and designing a soft robotic swimmer. On the small scale problems, CAPO is 300 to 300 times faster than the other approaches, but what you'll see is that it doesn't always find the sparsest configuration of designs, and that's okay because CAPO is not the silver bullet for all design optimization problems. Where it's kind of specializing in is in these large scale problems where there's lots of discrete choices between the number and types of actuators. And we see that CAPO finds a sparsification of around 15 to 30%, where the other algorithms fail to propose any solutions to these high dimensional problems. And so the key takeaways from this initial work is that by introducing this discrete parameter, we can decouple the control optimization and actuator placement problem. We can solve these problems with a relaxed method, but still satisfy the original constraints of actuators existing and non-existing, we can identify robust configurations by optimizing over multiple trajectories, and we find a sparsification of these solutions. And this kind of leads back to my initial thesis statement showing that CAPO can find high-dimensional task-driven designs, enhancing the engineering capabilities for designing these complex systems. And it works on a variety of different design optimization problems, not just the single problem that we presented today. So while CAPO was amazing with its actuator placement task, it only captures this high-level behavior because of the bulk modeling and the kind of specifications of the problem. But really, the interesting aspect of James Webb was all of its deployment capabilities and the link-level interactions that occur. And so in this next work, I'll be presenting an efficient RL-based optimization approach for large-scale linkage graph optimization. This work was published in the Journal of Mechanical Design and was awarded the ASME JMD Best Paper Award in 2023. So linkages, like I have many in front of me here, are these systems that translate rotational motion into some sort of desired output. We've seen these in our windshield wipers or other sorts of everyday systems. However, they're also used in the design of these complicated systems like the James Webb Telescope or the Strand-Beast. Now, the forward design is I have this linkage and I'm generating this output path for a particular task. But typically, we know what the output path wants to look like, but we don't know what the linkage graph to generate that output will look like. And this is called path synthesis in the linkage design world. And we can set up this problem again in this optimization formulation. In this case, we present GCP Hollow, a high-order linkage graph optimization. We have our 4-bar linkage here, which is driven by a single motor actuator and generates this coupler path. And what we're trying to do is we're trying to minimize the distance from the coupler to some sort of goal design that the engineer might put forward. We need to make sure that our linkage obeys the degrees of freedom. It's only a one input system and obeys all the kinematic constraints, meaning that it doesn't pull itself apart or break during the general motion. In this problem, we can move the different revolute joints that are these little circles connected by those rigid elements. And we can also change the number and connectivity of these elements that construct the linkage graph. Now, the linkage is a real physical system, but we can represent it as a mathematical graph, which relies on two matrices. We have this adjacency matrix, which has a bunch of zeros and ones that tells us how all of these revolute joints are connected with each other, and this node feature vector called V, which is the time-varying position of all of the revolute joints. We need to make sure that our linkage graph satisfies these constraints, and you might think we can apply the same algorithm we did for CAPO to a problem like this, but those specific tricks and heuristics do not necessarily translate to this problem easily. And so we actually used a different approach for solving this through sampling-based methods, which allows us to satisfy these constraints very quickly, and we can evaluate this goal very much more efficiently, especially as the large number of connectivity and links grows, the optimization problem balloons and can take forever to find efficient solutions. So through sampling, we can always support obey the degrees of freedom by just adding 0 degree of freedom extensions onto the linkage graph. However, this is only one instance of the linkage. Remember, these are moving and changing over time, and so we need to make sure that this addition satisfies all of the time-varying positions. And so to that end, when we look at two of these revolute joints and their trajectories shown here in yellow, we can look at a variety of potential positions to add these extensions and validate which ones are going to be kinematically feasible, and then add our final extension, making sure that all of the intermediate graphs and linkages are valid for construction. And so this looks like a tree search. We can generate a large corpus of potential designs that may be extended. And one of the ways that has been shown to be very efficient in finding solutions in these large tree-like problems is through reinforcement learning with programs like AlphaGo. And so we built our own RL agent that can find a search heuristic through this design tree that can efficiently find the minimized coupler position. So the RL agent is a graph convolution policy network, but what you need to know is it takes in the graph state, the adjacency matrix and node feature vector. It converts that into a lower dimensional representation through a graph network. And then we pass it into this, black box agent that promotes an action, which then gets evaluated on our reward, which is how close are we getting to our desired goal? And do you actually obey all of the laws of physics and degrees of freedom constraints that we've set forward? If it does a good job, we give it a wonderful reward and pass the next state back into the RL agent, and it continually learns this heuristic over time for finding good solutions. So we compared this sampling-based method with some of those mixed integer approaches, as well as a different sampling-based approach, and we found that GCP Hollow is 13 times faster in all of the 8 test cases, but it only performs better designs in about 50% of the cases. And that's because the sampling-based approach is stochastic, it's non-deterministic. It might, given the same problem, find a different solution to the initial request. And so in many cases, we are able to search larger and more complicated linkage graphs, but we're not always guaranteed to find the best one. So looking at what GCP Hollow contributes, this generative AI method promotes fast generation of rapidly producing kinematically feasible linkage graphs. And by using a sampling-based approach, we can keep all of the corpus of potential solutions versus the gradient-based approaches that offer us only one particular linkage graph to support the design. And so going back to our Venn diagram of how we can enhance physically intelligent systems, we see that GCP Hollow can find these high-dimensional task-driven linkages, supporting the development of linkage-based systems, hopefully designing more robots that leap off of walls and look like the Salto, or walk on beaches like the Janssen robot, or developing these next-generation deployable space systems. So all of the math mostly is done now. We've gone through the tough design optimization, but the solutions that we found only look feasible. They don't necessarily translate to the real world. And so this next half of the talk is going to be, how do we support the translation of these optimization solutions into physical systems, improving the reliability and the realism of our products? This next work was in collaboration with my dear friend and collaborator, Dr. Sawyer Thomas, on a hierarchical composition and integer optimization for novel mission constraints. This work was presented at the IEEE Aerospace Conference, and a journal version is being under review at Communication Engineering. You might have heard about the amazing, or the astronauts that were stuck in space recently in the February mission that caused them to be brought back home. There was a lot of drama in the news. However, the most significant thing was the health concerns of the astronauts extending their stay in microgravity environments. It degrades our bones, our eyes, our ears, and there's major concerns. The longest an astronaut has ever stayed in microgravity is over a year, and it was a Russian cosmonaut that got stuck during the fall of the Soviet Union. So to support astronauts and mission planners for these long duration missions, for example, going to Mars takes 7 months just one way. And so how are we going to be able to support the human capital and human people that we are sending on these difficult and important missions, and making sure that they're safe along the way? And so to that end, we need to create a artificial gravity structure through a large deployable mechanism, which we'll talk about now. And just for context, we're talking on the scale of 45 times the size of the James Webb Telescope. So artificial gravity sounds like science fiction, but it's really just the result of centripetal force. We've probably all been on a roller coaster and felt how the body feels as it's spun around, being pushed back on itself. And what really is happening there is just we need to make sure that the spinning doesn't also cause residual nausea or disorientation. And so to be able to create enough acceleration but spin slow enough, human factors research shows that we need to be at around 1 rotation per minute, with 2 being the absolute limit for humans to sustain long duration spinning effects. Now, to fit a kilometer scale structure in existing or under development future space vehicles, we need it to collapse or deploy on the order of 30 to 100 times its full size, as these rockets are quite large, but the stowable space is actually much smaller. So we looked at the history of deployable space structures, from inflatables, elastic, pantographic structures, telescoping tubes, and we saw that none of them were really able to satisfy all of the harsh requirements of this particular problem. And so we developed this hierarchical approach that combines multiple deployable structures together, which we call herds. Now, there's many ways that you can develop herds, but we'll show a couple of examples today. The first, we combine the combination of the Kressling mechanism, which has a twist extension coupling. Feel free to pass this around, with a pop-up extending truss, which collapses to 50% the size of a scissor-based system, with improvement of 100% in the bending stiffness of the structure. And when we combine them together, what we're able to achieve, and I'll lift this up so people in the back can see, is we get this twist extension from the Kressling and the physical extension from the scissor mechanism, which gives us these really efficient stowing behaviors for, I got some more with that. We get these really efficient stowing behaviors that allow us to achieve these 50 to 100x extension ratios that we're looking for. So because we've composed these 2 independent deployable systems together, we now have more knobs to tune and change. And so the engineer can then optimize the configuration of these independent structures to satisfy the various constraints and goals. So we want to maximize or minimize the stow volume to the strength, while obeying the fairing diameter and height and mass limits, and obeying all the other potential mission constraints that we're looking for. We can vary the link lengths and thicknesses and the number of scissor units in the Kressling mechanism. Now, we can't necessarily test the strength of these structures. We usually do that through FEA approaches, which don't naturally fit into gradient-based optimization. So we introduce this heuristic of minimizing the member aspect ratio, which should guide the optimization towards stiffer solutions. And when we look at the hierarchical structure compared to its independent components, we do see an improvement of member aspect ratio of the order of 4 to 12 times. But as I mentioned, we do need to understand the actual strength of this structure. This is only a proxy for strength. And so we did an exhaustive design sweep over the thickness and deployment angle, as well as the member subcomponents. We compared the structures in compression, tension, torsion, and bending. And what we see is that the high extension ratio structures where we're able to achieve the kilometer scale deployment, the herd systems are orders of magnitude better than the non-hierarchical approaches. But as I mentioned, we need to translate these solutions into the real world. And so we built a 1/10 scale prototype of the physical system, which consisted of 1,500 individual 3D printed components that meticulously hand assembled by many of my lab mates who are here today. So thank you so much for allowing us to achieve this amazing structure that goes from 2 inches on the order of 8 feet tall when fully extended. And when the system is locked and then loaded, we're able to support 15 pounds of compressive load and 10 pounds in bending, which is pretty impressive for a 3D printed structure. In additions, you guys, many of you see the kind of advancements we've made to these structures since then, and we definitely can hit the 100x extension ratio needed for existing space vehicles today. So through hierarchy, we're able to extend the capabilities of these linkage-based systems, showing that the composition provides a high strength to stowage ratio. We can leverage our design optimization tools to help the engineer design these systems for specific mission constraints and downstream tasks. And the realization of these physical systems demonstrate how they're able to perform in the real world, translating these optimized solutions into physical products. Leading back to my thesis statement, how hierarchical composition enables these mechanically stiff structures. Now, for next generation design engineers, you don't have to just think about this simple problem of the expanding deployable pole. We can think about other sorts of interesting ways to apply hierarchical extension through next generation telescopes, or even as the basis for ultra compact robotic arms and grippers, or for disaster and defense applications for generating collapsible bridges. So like the James Webb Telescope, this required a lot of that good old-fashioned engineering, which is cost and time intensive. And what we were doing this, we were wondering, how can we leverage some of that testing to extend our ability to evaluate these systems more efficiently? And so to that end, we wanted to combine data and simulations so that we can have these tools to extend the testing of linkage analysis. And this will be faster and more efficient, as well as safer. We can't always test our systems to the extreme. We're not building 2 James Webb telescopes to destroy one and see how the other one is going to perform in space. And so this next work works on a numerically stable differentiable simulator for linkage-based systems. It was presented at the IEEE Aerospace Conference this year. Now, for those that don't know, IEEE Aerospace always takes place at Big Sky, Montana. And while I did not win the Best Paper Award, I did receive the coveted 3rd place in the downhill ski competition. So linkages, as we've heard throughout this talk, have many advantages. They're scale and material agnostic. They're simple to manufacture and assemble. They don't rely on material strain, so we can model them easily. And they're safe and prolific. We've seen many examples from retractable roofs to scissor lifts in construction, but still many engineers avoid them for space applications because there's force synchronization issues or large number of parts. There's jamming concerns and joint friction uncertainty. And so what we look at is, how can we leverage this data and simulation tools to understand the coupling of these specific parameters that emerge when we manufacture these structures, and how can we use that to help engineers design next generation iterations? Now, deployables are really critical for space applications, as they're usually related towards the power and communications of the systems, and failures in deployables can cause the whole mission to fail, leading to billions of dollars in losses. And one example of these potential failures is through the kind of stack up of the joint clearance and joint friction, which we can see here simply through the scissor mechanism. And so I'll pass around the scissor units so that you can feel the joint clearance and the flexibility. When we have this idealized scissor, everything opens up symmetrically and smoothly. However, when we add some joint slop to the system, we see additional resistance, this asymmetric deployment, and in many cases, many of the links don't deploy at all, leading to the potential failure of space missions. So we developed this framework that allows engineers to leverage the data and simulation tools to evaluate linkage systems on downstream tasks, making sure that we can understand if jamming is going to occur and how the force and torque requirements might affect the deployment. And then ideally leveraging that data back into the original design to iterate over these next generation systems. So to that end, we take our physical system, this flexible scissor model that was 3D printed, and because of the irregularities in 3D printers and the tolerances that we can achieve, we get this kind of interesting deployment behavior. We added a couple of springs on our test setup to kind of repeatedly and reliably capture data across multiple different trials. We can then extract that transitory information of how the scissor mechanism deploys using computer vision algorithms or other sorts of methods. And then from that, we can extract these state trajectory and control inputs, where we can hopefully learn the emergence of certain parameters like the joint clearance, X limit and Y limit, and any sort of dry friction parameters. Using our differentiable simulator, we can then play around with the different parameters to see how we can most closely match the real world data and the simulated data. And more explicitly, we can write this as an optimization function, minimizing those differences over time. Now, as I said at the beginning, there aren't these tools to natively support these large constraints and linkage-based systems, but we extended the capabilities of some of existing simulators developed in our lab at the Rex Lab called Dojo that supports these full SE3 representations. It's differentiable and handles contacts and joint clearances. And so by addressing the numerical challenges related to redundant constraints and what occurs when we have lots of links in the system, we can now simulate a large corpus of rigid body systems that were previously unmodeled. And the synthetic data shows us that our optimization quickly converges to a solution that looks very similar to the true synthetic scissor. However, the results don't necessarily look as promising, as the true joint clearance and true joint friction actually vary a little bit more than we would like, even though the position error of the system stays consistent over time. And that's because we're finding these local minima. What we discovered from this is that we need to actually test in a more diverse set of potential deployments so that we can decouple the joint friction and joint clearance, because maybe multiple combinations of joint clearance and joint friction can derive the same deployment behavior. When we look at the real world data, we see some more sim to real gap opportunities with the lack of consideration of how the links kind of contact each other. And so in the simulated one, we see the system stacking much more tightly than in the physical system. But even with all of these sim to real errors, we only have about 2 centimeters of position error. And at least qualitatively, we have the same number of scissor units deploying between the simulated and real solution. But what is most important about this tool is the ability to evaluate these systems in different conditions and making sure that we can understand the forces and torques, as well as any of the singular values that might occur from jamming. And this kind of pops up naturally from our simulation tool, where we can kind of monitor the number of singular values in the system, and this will allow us to detect the jamming occurrence. And here, more clearly, we can see that force synchronization issue, as the green lines are the estimated reaction forces at each of these joints. We see how they propagate through the system, leaving many of the scissor elements completely untouched. So the key takeaways is that data plus simulation allows us to support engineers' ability to safely test these systems under unseen loads and conditions, allowing us to capture joint reaction forces and joint friction that emerge from manufacturing intolerances as a wear, and leading back to our Venn diagram of the thesis, showing how these tools can enable the engineer to create a feedback loop of design, test, and evaluate more efficiently. And this extends to a variety of different types of deployable structures and linkage mechanisms, not just the simplified scissor unit that we tested today. And all of these tests, both the James Webb and in the scissor experiment, have to usually be done on Earth, as there's people that need to interact with these systems. And gravity definitely influences a lot of these parameters, as there is the bias of where those joints are going to kind of settle. And so this particular simulation can only really show that it supports on-Earth evaluation. But all of our systems we're hoping to deploy, and we've talked about today, for future space systems, which will be in zero gravity environments. And so we were fortunate enough to be awarded 2 research flights on this recent zero-G mission to capture these in-space behaviors in a simulated microgravity environment. Now, this work was happened just in the last month, and so I'll be providing some initial results and thoughts about the data that we were able to capture. This sim-to-real evaluation will be submitted to the International Space Robotics Conference this summer. We extend our design items beyond just the translational scissor towards systems like this polar scissor element, as well as these translational scissor elements. And you can see on those systems, as well as the pop-up extending truss, that there's a bunch of these stickers and IR markers, and that was to support our capturing of all of the data through our custom motion capture system. We had 8 GoPro cameras and 4 OptiTrack cameras to be able to get the high fidelity information we needed to verify our simulation tools. In the physical system can be seen in the top right corner. Now, it wouldn't be a project of mine unless there was a build montage with a lot of amazing lab members helping me out, building 10 of these pop-up extending trusses, which relied on many hundreds of parts and thousands of stickers being placed by hand on all of these systems. But we saw that with more people, it expands exponentially. A huge thank you and shout out to my master's student that supported me, Joe Kuhl, who helped on a lot of the design of the systems and developing deployment. So now let's take a look at some slow motion video captured from the recent experiment. First, looking at this translational scissor mechanism and the corresponding simulation I was able to generate. One of the interesting behaviors that we see here is its kind of reorientation after it deploys, this kind of twisting over itself that we still see here in the simulated model. Now, I wanted to show what happens when we change the friction coefficient and how that affects the deployment behavior in the simulation. We see that when we have the friction too low, the system will over deploy and collapse back on in on itself, versus when we have the friction closer to what the true value is, we get this more accurate deployment behavior. And then finally, looking at this pop-up extending truss, we see the really interesting behavior right here at the bottom at the end, where it reorients itself, and the same behavior emerging on the simulated model, where we can also visualize those joint reaction forces of the deployment of the system. So I'll let it play like one more time before we skip past this. Now, this was CMU's very first zero-G flight in the history of the school. And so the question we were all really wondering is, how is Scotty going to behave in a microgravity environment? And we were able to capture it from multiple perspectives to ensure the realism and reliability of the data. So a huge thank you to so many people for making this a successful mission. And thank you to the zero-G staff, the NASA people that supported our push for this project, and Zach, Jeff, Sawyer, and Joe, who helped collect all of that valuable data during the approach. So throughout this presentation, I've shared new approaches for linkage design through hierarchical composition. We've provided new methods of constraint-satisfying efficient optimization formulations for high-dimensional design tasks. And we've shown how data in differentiable simulations can be used to enhance engineering tools and analysis for next-generation deployable systems or intelligent robots in space structures. So looking back at our original inspiration of the IBEX and the amazing combination of physical intelligence with artificial intelligence through the SALTO and the James Webb Telescope, I hope you can see how the work that we've done is attempting to push the field forward in developing these more physically intelligent and capable systems. So I have a lot of people to thank, first with my collaborators, who have been very fortunate to work with every single one of my committee members. Minchen, thank you for the many debugging hours on the cloth simulation for figuring out why our state estimation wasn't working. Jeff, thank you for the last 3 years of both professional and academic advice. And John, thank you so much for the amazing 5 years. And the walks with Heidi will forever be, core memories during my PhD.
That's a dog.
Yeah. And then Zach, as you mentioned, it was, some sort of fate, or I don't know, maybe space gods coming down to bring us together. And thank you for giving me the longest rope to do whatever I wanted and pursue all of these amazing and interesting projects. Thank you to all my master's students, as well as all of the other amazing people that I've collaborated through this PhD. And of course, the sponsoring members, NASA and NIAC, have been absolutely critical for the success of all of this development. And I hope that they feel like they've gotten their money's worth. They've gone above and beyond to make sure that we were able to achieve all of these missions. Now, there's a lot more people, probably 90 more slides of thank yous that I could do, but I want to start from the beginning. My mom and dad, who are so fantastic and unwavering love, my brothers, who are my best friends and biggest inspiration, my grandparents, my cousins, and of course, my amazing partner who I met here with the copious amounts of brownies to get me through the tough deadlines. Thank you to all my lab members from IDIG and Rex Lab, and to the broader MECI community, who have just been absolutely my best friends and inspirations. Thank you to the people from Penn, like Aaron Johnson, and all the people from Cod Lab who inspired me to do a PhD. And of course, my Professor Bruce, who came all the way from Philly to come watch us here today. So with that, I'm opening it up for questions.